All right. Yeah. Thanks a lot for the introduction. As introduced, my name is Dominik Willenberg. I'm from RWTH Aachen University, and in the following, I'm going to present the content of my paper, Impact of Wind Turbine Generator Technologies and Frequency Controls on the Stable Operation of Medium Voltage Island Microgrids. So, as you all know, there's an increased penetration of distributed generation units, especially photovoltaics and wind turbine generators, and they're in the low and medium voltage levels. Throughout this development, there can be a local generation surplus in existing distribution grid structures, which opens the opportunity for temporary island microgrid operation. If we now think about this temporary island microgrid operation, there are quite differences if we compare it to the normal grid parallel operation. So first, there's strongly lower inertia, which leads to the situation that changes in the power balance may lead to larger frequency deviations. And also, these distribution grid structures are usually not designed for the temporary island microgrid operation. Moreover, if we think about the generation units existing in low and medium voltage grids, these wind turbine generators have, let's say, a significant impact on the power balance due to their very high power rating, for example, in comparison with, let's say, smaller PV units. Another fact is that usually two different types of grid coupling are used to feed in the grid. These are the DFIC and the full-scale converter in this case. So not only let's say the steady state or the normal operation is important to ensure in a temporary island microgrid operation, but also the stability must be ensured. So due to their high power rating, the stability supporting behavior of the WTG technologies is essential for stable operation. To maintain a stable operation, for example, in Germany, in normal or grid parallel operation, distributed generation units are obliged to support the grid frequency. This is done by here so-called frequency dependent active power adjustment, or in the following FDAPA, whereas the DG units have to adjust the active power and feed depending on the grid frequency. So when we have a look on the right bottom side of the slide, we see that let's say the frequency shown over the active power. And when the frequency changes, the active power needs to be reduced or increased. This figure on the right side is only applicable for energy storages, since they are able to consume power from the grid. So if we just think about generation units, due to the usually operation in maximum power point, only in over frequency situations they are able to reduce the active power. So not only this frequency control approach, but also the technology, since it's partly, in case of DFIC, it's partly rotational coupled to the grid and partly inverter coupled, have an influence on the stable operation, and it's necessary to determine how large this influence is. So if we think about the frequency control approach, as mentioned before, WTG units usually operate in normal operation at their maximum power point. So this FDAPA control approach reduces to a frequency dependent active power reduction. But here the question arises that this reduction may not be sufficient, of course, in under frequency situations. From the grid parallel operation, we know certain concepts, for example, the virtual inertia based frequency control approaches. And here the question arises, are these also applicable to temporary island microgrids in medium voltage level? Also, the differences in the technological options shows or opens the question, how does the technology influence the dynamic behavior? So that in the following and also in the paper, the assessment of the impact of the WTG frequency controls and technologies on the stable operation of temporary island microgrids is evaluated. Yeah, and first, the suitability of frequency support concepts is given by the grid codes and beyond is tested and validated. Then the impact of the different technologies is analyzed, followed by a verification of the introduced concepts by time domain simulations. And at the end, based on a benchmark MV grid, the mitigation of disturbances is evaluated. So concerning the modeling approach, first of all, to operate an island microgrid, it is necessary to have a grid forming unit. In that case, a synchronous generator of 6-order model is used, of course, with the necessary controls concerning site and governor. Moreover, its first technology of the WTG and DFIG is modeled, where an induction generator in parallel to a converter is built up. This model is expanded by an FDAPA control approach where the active power set points is adjusted when the frequency is changed, which is measured at the grid connection point. Moreover, also the wind turbine control, speed and pitch controller are implemented, and also the mechanical part is included. If you compare this with the second technology, the full-scale converter WTG, here, a controllable current source powered by a DC voltage source is modeled. The wind turbine model is set as a rotating energy storage, and also the rotor speed controller is modeled as a PI controller. The other grid components, for example, the load, are modeled as a ZIP load with a frequency dependency. The electricity grid is modeled as a P-equivalent grid model, and the dynamic simulations are based on a steady state operation point determined by prior power flow calculation. So all the results presented in the presentation are performed via time domain simulations. If we have a closer look concerning the FDAPA approaches, the medium voltage German grid code for inverter interface DG units states that an adjustment of active power output is necessary when the grid frequency is outside a specific deadband, in that case 49.8 Hz to 50.2 Hz. This is usually done by a droop value, which specifies the amount of active power which needs to be reduced per Hz. This is usually, this needs to be set following the grid codes between 2 and 12%, and the usual default value here is 5%. So when we consider just the situations that there is a reduction due to over-frequency situations, in this case the pitch controller reduces the extraction of the wind power to maintain the rotor speed. When we have a look at under-frequency situations, there VI-based concepts like FDAPA VI-based here is used. And here it is the situation that after the exceedance of the frequency deadband, so below 49.8 Hz, the active power is increased. This is performed as long as if the frequency reaches the deadband again, or the rotor speed reduces below a minimum value. This leads to a situation that when these cases are reached, that the WTG speed controller decreases the active power in feet below the initial value in steady state, so even below before the under frequency situation occurred. This is called speed recovery mode and has the aim to accelerate the turbine to its initial speed again. Usually, hand in hand with this comes the speed recovery peak, so a second dip of the frequency. Especially for or in grid parallel operation, to overcome this issue with the speed recovery peak, VI-based concepts with, for example, deadband hysteresis are used. So the idea here is that a smoother transition from this grid supporting mode to speed recovery mode is possible, and this is performed by just shifting this limit frequency closer to the nominal frequency, in this example 50 Hz. and to expect a lower speed recovery peak. So now to analyze the different impacts of the different control approaches, case studies are performed. Generally, a DG outage or load disconnection is simulated, which is equal to a load step after 1 second. Moreover, a constant wind speed of 10 meters per second is assumed, so that no activation of the pitch control in case of higher wind speed needs to be performed, and also the evaluation of the maximum contribution of the different control approaches is possible, which would of course not be possible in case of lower wind speeds. The validation topology is shown on the top right side, where we have a 3-bus MV temporary island microgrid. At bus A, we have the grid-forming synchronous generator with a nominal active power of about 2.5 megawatts. Bus B is a half industrial and half residential load node, where the load equals the total active power and feed of synchronous generator and wind turbine generators before the load step. And at bus C, the wind turbine generator technology, so in that case DFIG or a full converter wind turbine generator, is connected to. The cases that are simulated are 4 kinds. Differences between the FDAPR and VI-based FDAPA are analyzed, technological differences, parameter variations, and also the FDAPA with deadband hysteresis is examined and evaluated. In the presentation, I will focus on 1, 2, and 4. To identify if it's possible to mitigate disturbances by parameter variation, a modified Segre European MB benchmark grid is set up, where we have additional wind turbine generators at the nodes 1 and 12, and no additional DG units. This is done to solely determine the impact of the WTG generators. It is chosen a high load scenario. For the simulation cases, parameters such as the control parameters for the different FDAPA approaches are changed. General, just wind turbine generator parameters are changed, and also differences in the topology are simulated. So if we start with the simulation results and have here an over-frequency situation. So this is done to validate the FDAPR of, in that case, the DFIG. So what we see here is on the right side, the topology which is used. So each, the synchronous generator and the wind turbine generators have a set point in active power feed in from 1.2 megawatts, and a load step of minus 0.3 megawatts is performed. The droop value, in that case, the default value, is set to 5%. If we now have a look on the results, here shown with active power in red and frequency in blue, with and without FDAPR, we see that the frequency limitation or the violation of the frequency limitation is avoided by using this FDAPR control approach. Moreover, also occurring frequency oscillations are suppressed. So if we now consider the same scenario, but in that case with a load step of plus 0.3 megawatts, it is possible to validate the VI-based control approach. So what we see on the bottom right side in the figure is that again, also the depth of the frequency peak is reduced, but what we also see is that the second frequency peak occurs, especially if we compare it to the FDAPR approach. So it is necessary to determine a trade-off between the reduction of a peak and the speed recovery time. If we have a closer look right at the beginning when the load change occurs, we see also some technological differences due to the DFIG situation, that there is partly a rotational coupling and partly an inverter coupling. What we see is that there is a direct increase of active power throughout the direct coupling of the rotor. But if we also compare this with the frequency, we see that it has almost no effect on the frequency change here. If we then have a look at the FDAPA control approach with deadband hysteresis, we have just the change that when we consider only the VI-based FDAPA control approach, here a maximum of 2% of the maximum rotational energy is allowed to extract. To determine the maximum effect of the deadband hysteresis, for these simulations, this value is increased up to 20% to prevent switching to the speed recovery mode before reaching the deadband. This is performed for 3 different frequency limits. If we now have a look on the right side, we see that in comparison to only the VI-based FDAPA control approaches, there's no decrease of the speed recovery peak, so of the second frequency peak. What we only see is that it is shifted in time, and in worst case, it's even deeper than the first frequency peak, which leads to the situation that the SRP may become more critical. If we finally have a look at the mitigation of disturbances by parameter variation, consider here the medium voltage benchmark grids. And what we did is a variation of parameters here shown as in the results exemplarily increased by 20% for each parameter. So as mentioned before, the FDAPA control parameters are adjusted, the WTG parameters are adjusted, and different technologies are used. So the standard case is here 2 DFIG WTGs, one at node 1 and one at node 12 are used. So if we compare all the different grid frequencies over time, we see that variation of the FDAPA parameters and the utilization of both technologies splits the speed recovery peak into 2 less critical peaks. This can also be seen, let's say, in the yellow line seen, or the lines related to the changes in FDAPA control. There's almost no beneficial effect when varying WTG parameters, and most important is that different parameterization and different technologies improve the frequency behavior in this case.
Please, Dominik. Okay, the last sheet.
So it would be the last slide. So to conclude, the FDAPA in over and under frequency situations shows a stability supporting behavior. There's only a marginal difference between different WTG technologies, and the diversity of technology and frequency control parameterization leads to a more stable operation. As an outlook, since all the results were performed in simulations, a laboratory or field testing for real-life verification is necessary. Also, maybe interactions between different additional distributed generation units needs to be evaluated, and maybe also a combination with the demand-side management is possible. So that was my presentation. Thank you for your attention, and I'm looking forward to your questions.
Yeah, thank you very much for your interesting presentation of your research work. I open the floor for hands up and mention your questions, please. Or send your questions to the Q&A. Dominik, I have a question to you. In the beginning, you mentioned that you look to the grid code and beyond. Do you have some recommendations for such kind of microgrids? It's not usual in Germany to have microgrids. Concerning the grid code, should be something adapt in future, changed in future, to make islanding and microgrids possible in Germany?
That is actually a really good question. I think it's definitely not easy to answer this. From, let's say, a research point of view, I think it is definitely necessary to do this. Because if we would have a situation where, for any reason, there's interruption of supply from, let's say, the high voltage or extra high voltage level, it is possible also right now, there are already, let's say, research projects going on to supply certain grid areas just with the, let's say, existing distributed generation units or with the general generation units that are installed there for a local area. And I think this is, this is somehow quite important because in case there's only an initial interruption of supply for, let's say, only a few hours, I think this is not a problem. But if we think of interruptions that last, let's say, half a day, or even longer, then this really can be a help just to provide some electricity to the consumers to, keep the information flow maintained somehow in a way. So from my point of view, this should be included, but it is definitely a large challenge because usually the grid codes want to avoid this situation that we have islands, usually then they call it unintentional islanding. So that this is definitely not an easy way to go.
Yeah, thank you very much. Are there some questions more for Dominik from your side, from the audience side?
All right, I will just read it out. All right. So the question is there an impact between the rated power dispatchable CHP unit and the current available output power of the wind turbines? Yes, definitely there is. This is actually, maybe I'll just go back to, this slide. This is actually also something we investigated, of course, here just exemplarily. So what we see here is on the z-axis, the first frequency peak that occurs. And on the, let's say, bottom axis on the left side, the active power in feed of the synchronous generator. And on the right side, the active power in feed by a defig in that case. And what we see is that for example, in case of really small infeed, for example, of the synchronous generator or the CHP in that case, that we have here control instabilities, which means that not an, again, let's say steady state operation is possible, at least due to our simulations. What we also see is that if we have a really large or high infeed of active power by the synchronous generator, which is, let's say here the orange dots, which is really close to the operational limits of the synchronous generator, is again, let's say, kind of critical because it is not possible to, let's say, really flexible increase the active power over a certain value. So then here again we have a limitation somehow, which then leads or may lead to an exceedance of the frequency limits. So yes, there is definitely an effect here.
Yeah. Thank you for answering.